Hi, good morning. In this video, we can evaluate the equation for heat transfer across the regular cylinder. The heat is transferred from inside cylinder to outside atmosphere. See, this is the front view of the cylinder. It is having hollow space. In this, assume there is a hot liquid or hot region it is having. This is at higher temperature T1, and this is the rigid wall. This across this wall, heat is dissipating in radial direction. So in all radius directions, heat is dissipating to the atmosphere. This is a hot body, this is the cold body. So outer ring is at cold region, inner region is at hot side. So for this you have to draw the one strip of element that is in circular shape with radius r. This is the radius r. With radius r, with thickness br, draw the one differential ring. This is the outer radius r0. This is the inner radius of the circle ri. This is the radius at where we are considering the heat transfer rate. Come to the Fourier's equation of heat transfer. Fourier's heat transfer equation. So what is Fourier's heat transfer equation? This Q is equivalent to, so this is the heat transfer from cylinder to outside. From here it is transferring like this. Here to here it is dissipating. This is Q. Assume section, this is point 1, this is point 2. In between point 1 and 2 heat is transferring. That means this is the temperature difference from T1 and T2. This differential ring, here we are having thickness. This is the gradient of temperature dt. This is dt, this is dr. When you apply this equation, that is heat transfer equation of Fourier's, that is Q is equivalent to minus K A dt by dx. So x is in the direction of polar coordinates, that is in radial direction, in this direction, anywhere in the radius heat is dissipating in all sides in radial directions, only one direction. So this is assuming it as one dimensional and steady flow. That means steady means dt by temperature change with respect to time is 0, and one dimension means in another directions, that is in L direction or some Z direction, there is no heat transfer in any direction other than radial direction. So heat is transferring in only one direction, that is in radial direction. So we can write this as minus K. This is heat transfer conductivity, thermal conductivity of the material of the cylinder, K. Then area of cross section. This is the total area from here to here. Say this is having a length of L. It is length of L, or height of cylinder H. Then this is the area of the periphery, peripheral area, peripheral length into length of the cylinder gives the total area of heat transfer. So that is the area of heat transfer is 2 pi r is the peripheral length. This is the peripheral length from here to here. Then how much depth? That is L depth into L. This is the area into dt, temperature change. So this is temperature change dt here to here for small strip, divided by this is the r. How much length? This is dr. So this is the Fourier's equation of heat transfer, and rewrite this like this. Pull this side, Q into dr by r is equivalent to minus k 2 pi L dt. Integrate both sides by applying the limits. So heat transfer is constant, right? We are transferring heat or dissipating heat from inner to outer into this dr divided by r integration. Integration limits, radius is varying with respect to r. We are doing the integration. So radius is, limits are ri to r naught. So ri to r naught is equivalent to minus k 2 pi L integral dt. So temperature is varying in between T1 to T2. These are the limits. So it is varying from T1 to T2. Pull this, Q is the constant, apply. This is dr by r, ri, r naught is equivalent to minus, this is also constant, minus k 2 pi L is not varying, it is not variable, L is also constant, length of the cylinder, integral, this is T1 to T2 dt. Integrate this, we will get Q into this 1 by r dr is log x log r base e. Log r base e you can write as ln r. Apply the limits. This is ri r naught is equivalent to minus k 2 pi L into integral dt is t. Apply the limits 1 to T1 to T2. Then substitute the value Q into ln r naught minus ln ri is equivalent to minus k 2 pi L T2 minus T1. This is the top view. Okay, this is the front view. This is front view, this is top view. Don't get confused. Then Q into algorithm algebra, log algebra, we can write ln r naught minus ln ri. We can write ln r naught divided by ri is equivalent to, here minus, you can change, this is the T2 is lesser than T1. T2 is lesser than T1. So it will give the negative value. So negative of negative, when you apply on T1 minus T2, so you can get minus get cancelled. This is minus k 2 pi L T1 minus T2. We can write T2 minus T1 is the negative value. When you apply like this T1 minus T2, you will get you are going to get minus plus. So you can write as T1 minus T2. Then therefore Q is equivalent to K 2 pi L T1 minus T2 divided by ln R0 by Ri. This is the equation for heat transfer in cylinder in radial direction from inner to outer. Then what is the thermal conductivity? So this Q is equivalent to T1 minus T2 divided by, we have to find the thermal resistance, that is RTH. Q is equal to T1 minus T2 divided by thermal resistance. It is analogous to, heat is analogous to current in electricity, electrical current. It is the potential difference, here it is the thermal temperature difference divided by thermal resistance. So both are analogs. That's why the same network concepts will be applicable for heat transfer also. Then what is the thermal resistance? That is, you can write it as R ln, that is ln R0 by Ri divided by this 2 pi KL, 2 pi KL. This is the thermal resistance. So this is equation 2, this is equation 1. So like this we can derive the equation for heat transfer from inner to outer side across the cylinder wall. We can derive or express the equation by integrating Fourier's equation by applying the limits R0, Ri and T2, T1. Thank you for watching.